Hi, everyone. So in this video, I'll talk a little bit about some of the terms that we've gone over in lecture on graphs. There's a lot of new terms that come out. I want to start out, though, I want to remind everybody just what is a graph. There are a lot of different ways of representing graphs. And when I say what is a graph, I mean for our course, there are different types of mathematical graphs that are studied in other courses and may be studied later on in this course. But right now, what we're talking about is a graph with vertices and edges. And these are the two things that will describe the graph completely is the edge list and the set of vertices. And so I'll just represent my graphs by drawing little dots and connecting them. So let's say I have 5 dots and I can connect them through edges. That's what we typically want to write when we're writing a graph. Sometimes these edges cross, and so you have to be a little bit careful about what your vertices are. They're not the crossings, but rather just the dots. So let's say A, B, C, D, E. Okay, and the edges in this graph, you can list them out. If we count them, we see there's 1, 2, 3, 4, 5. And yeah, just counting them, we can write them out for the edge list here, AB, BC, BD, CE, and BE. Sorry, let me move this over a bit. I'm running out of room. So BE. Okay, so this is your edge list. And something I mentioned in a lecture, but maybe your instructor will also mention, is that you can write down a different, or you can draw a different picture. Let's say we had A, B, C. I'll still label these dots A, B, C, D, and I can draw a picture A, B, B, C, B, D, C, E, B, E, and you may say, okay, well, if I look at this second picture and I look at the first picture, they look very different, right? I mean, the first picture, all the edges are straight line segments. The second picture, they're poorly drawn, and so you might say, well, these are definitely different looking things. But the idea of what we're studying in this section and what graph theory people study in general is that typically are not, at least initially, not looking at the pictures. The pictures are a visual representation. These are sort of the same graph because they have the same edge list and they have the same set of vertices. Uh, so, so these are all pictorial representations. Some people study those representations, but we're not looking at that right now. Okay, so with that out of the way, let's just review a few different terms that people use when they're talking about graphs. So one term is like adjacency. And you can sort of use it with regards to two vertices, an edge and a vertex, or two edges even. So you can say, well, one or two vertices adjacent. They're adjacent when there's an edge connecting them. So D and B are adjacent. Great. You can also say, well, I've got this edge here. It's adjacent to C. Sometimes you'd say incident. That's fine. But sometimes you just say C is a vertex of this edge. That's okay too. But sometimes people use adjacency there. You also talk about edges being adjacent. So for example, AB is adjacent to CD, BC, pardon me. So these two edges are adjacent because they share a common vertex. On the other hand, AB and CE, they're not adjacent. They don't share any common vertex. So no dice. So there's this notion of adjacency. Those kinds of terms are used as well. The book deals with more general graphs. What I've drawn here is called a simple graph. And again, simple graphs are not necessarily that simple. They can be quite complicated. But what simple means here is it means that given any two vertices, there's at most one edge connecting them. So there's not multiple edges. You can certainly draw if you wanted to, and I'll draw it and erase it. You can draw a picture like that, where that's indicating there are two edges between A and B, and then you in the edge list you just write AB twice. It's a little confusing, but it's possible. Another thing that is not drawn in this particular graph is a loop, and a loop is just some edge that starts and ends at the same vertex. So we call this a loop. So that's those two things definitely occur, and that's a part of the vocabulary. Um, what else? Well, there's several terms, but I want to kind of draw your attention to notions of some important notions that we talk about, and that sometimes people get a little lost on. So one is the notion of a path. Okay, so what is a path? A path is you can think of it in one of two ways, and I'm going to think of it a certain way in this review. I want to think this is a sequence of vertices. Okay, and I'll label those vertices. Um, let's say V, the zeroth vertex is V sub zero. The second vertex is V sub one, so I'm always kind of indexing one behind. The third vertex is V sub two, and then I'll end at the nth vertex, V sub n. So these V's, they are vertices there, and I'll write down an example in a second. Okay. All right. But they're not any sequence of vertices. They have to satisfy a couple of properties. So such that whenever I look at two in a row, the ith vertex and the I plus first vertex, these are distinct edges of the graph. So that may seem a little abstract, but I'm kind of cramming two properties into one here. I'm saying that when I look at two in a row, that's an edge of the graph. So the first two, V naught, V1, that's an edge. Second two is an edge, so on. But then I use this word distinct, meaning that each of those edges aren't just edges of the graph, they're all different edges of the graph. So I don't repeat in this sequence. And this notion is the notion of a path. So this whole thing is the notion of a path. So let's see an example here with our sample graph here, our simple sample graph. So for example, uh, well, I could do something like A, B, C, E, B. That's actually a path, okay? And let's trace it out. Basically, it's saying, okay, start at A, go to B, that's the second, C, E, B. Okay, I've each time I've taken a step, I'm an edge in the graph, and each of those edges are distinct. They're different. So that's what I need to satisfy. Right. So what is what are a couple of non-examples? So non-examples, meaning examples where we would write down a sequence and it's not a path. I could do something like A, D, B, right? That's a sequence of vertices, but when I try to go from A to D, there's no edge connecting A to D. So this is not a path. It's a sequence of vertices, not a path. Another non-example would be maybe the one I just had that was a path, but I decide to keep going. Sorry, let me move my picture down so that I can refer to it. So sorry, let's see. So I decide to keep going, and I go to C. So you might say, okay, well, let's give it a try. I go from A to B. I go from B to C. I go from C to E. I go from E to B, and then I go from B to C. And if you were following what I did, you'd say, well, each time I took a step forward, I have an edge. However, if you do it all at once, you'll see something. I go A, B, C, C to E, E to B. And that last step is I'm repeating an edge. So this BC edge, I've gone over it twice. And that's not distinct. That's not a new edge. It's not distinct from that edge where I already crossed it. So this is not, both of these, not paths. This one, it is a path. Okay, so paths are important because we do look at Euler's theorems and Euler paths, and that's something that we spend a little time on studying in this course. So what's some other, I'll get to that in a moment, but let me ask some other basic properties. So there's another basic thing we look at is we look at the degree of a vertex. And the degree is not, there's, if I give you a graph and I say, what's its degree? There's no degree of a graph. There are some variants. Maybe you could talk about the maximal degree or the minimum. You could talk about regularity. You can talk about other things. But when you talk, typically when you talk about the degree of something with a graph, you're talking about a vertex in a graph. And how do you calculate that? Well, the degree of a vertex, if I just chose vertex B, for example, is I just count the number of edges that have B as one of its vertices. So I've got 1, 2, 3, and 4. So the degree of this is 4. So this is what I want to say here is the number of edges with that vertex, So again, in this case, we would say that the degree of B equals 4. The degree of D equals 1. And the degree of C, for example, is 2. Okay. And again, that's because D only has one edge coming from it. C has 2 edges connected to it. So that's the degree. Returning to paths, there's a notion of connectedness. So we can also talk about connected versus disconnected graphs. And connected, it means that you can't, I mean, its notion is that you can't take the graph and pull it apart without sort of breaking it. And the rigorous way you can say that is if I have any two vertices in my graph, there's some path that connects them. So this means any two vertices, not just some, can be connected by a path. And disconnected just means not connected. In other words, there are two vertices that can't be connected by a path. So this example here is certainly a connected graph. I can get from any vertex to any other vertex, and I'm doing great. On the other hand, if I took this example and I just even did something really, I can do a lot of silly things. It's not too hard. So I could, for example, I could draw another, I can add another few vertices. Like let's say I put some kind of triangle graph. I need to put H here. I'm just gonna put J, but I don't know why I got H. So I have some, and I consider now this whole thing, you may say, well, you have two graphs. Okay, maybe. But if I draw all of these vertices there, I can say, well, this is my graph. Graphs don't need to be connected. I can say, well, no, I've got a graph. It just has two, it's just disconnected. And there's these connected things are called components. So it has two components. So uh, it depends on how you look at it, but typically a connected graph is what you typically are dealing with. But the reason you want to maybe have this language is sometimes you can do things to a graph that would make them disconnected graphs. And so an example of that is removing a bridge. So let me give I'll give a particular fun, I don't know if it's fun or not, but I'll give an example. So let's say I have something like this. I've got three triangles floating out here. And then I've got some vertex here. And I connect them like this. And I'm not going to label the vertices for the moment. I'll just draw the picture. And this is a connected graph. Any two vertices, as you can see, you can find some path from one to the other. And however, there are some special edges in there called bridges. So let's say I ask you to identify all bridges. Well, what is a bridge? If this is my question, um, the answer will be to find to go ahead and um, find those edges that I'll say edges in red. Find the edges that when you remove those edges from the graph, you have a disconnected graph. So this is a connected graph, but if I take out an edge, it may all of a sudden become connected. So let's say I tried this with, say, this edge. I remove the edge. Well, it's still connected. I can still find a path between any two vertices. So that's not a bridge. However, if I took this edge away, all of a sudden I have a disconnected graph. So this edge is a bridge. And when I have such a thing, I'll color it red. If you look, you might be able to find the other bridges. And indeed, they're kind of, there's sort of a little bit of a symmetry here. They're right here. These two are both bridges, and everything else is not a bridge. So bridges are not too hard to find unless the graph is really, really complicated looking, and then sometimes it can be a little tricky to look at the picture and find them. But there are it's not too bad. There's some ways of doing it computationally as well. All right, great. So let me then kind of end this review with finding Euler circuits and identifying our Euler paths. So I talked about a path up here, sorry. And in this path, we have sort of a beginning and an end. So paths are sort of oriented from the first vertex to the last vertex. So we have the starting vertex and the ending vertex of a path. And when it turns out that the start and the end are the same vertex, when you kind of get back to where you started, we call that path a circuit. So let me just say that, write that down. If beginning, or say start equals end, we call it a circuit. We call the path a circuit. So great. And so now what is an Euler path or an Euler circuit? So an Euler path is a path whose edges are all of the edges of the graph, of the edges of a graph. So in other words, it's a path that when you complete the full path, you've hit every single edge. And the same notion, I won't write it down, but the same notion is for a circuit. It's a circuit in which every single edge of the graph is hit by the circuit. So Euler's theorem tells us when we have and when we don't have an Euler circuit or an Euler path. There are two theorems, and what I won't go over that theorem, but we'll look at it in practice with with a couple of examples. So let's take this example here, and let's see if we can find an Euler circuit for this guy. And so what Euler's, I'll go over what Euler's theorem says, but I won't go over kind of any of the arguments here. What Euler's theorem tells you to do is first find all the degrees of your vertices. So I'm going to write those in red. I've got A is degree 1, B is degree 4, C is degree 2, E is degree 2, and D is degree 1. And then Euler says, okay, if you want a circuit, the only way you're going to have one is A, if this is a connected graph. Okay, it's connected. Yes. And then B, if I'm looking for a circuit, an Euler circuit, I need that every single vertex is even, meaning that the degree of every vertex is even. I'm out of luck. So these guys are odd, A and D. And so I have a couple of odd vertices. I definitely don't have an Euler circuit. So no Euler circuit for this guy. However, all is not lost. I just looked at them. We have two vertices that are odd, and all of the other ones are even. So in fact, there is an Euler path. So there's some path. And furthermore, Euler's theorem says that there's a path which starts at one of those odd vertices and ends at the other odd vertex. And to find it, all you have to do is follow Fleury's algorithm. So, and I'd encourage you to look in the book or go to the class or watch the videos if you have some to see how Fleury's algorithm works, but we'll go through it really quickly. So what does Fleury's algorithm says? It says start where you're starting. If you're in the path case, start at the start, and then you want to choose an edge for your first edge of your path. And what you choose is you choose an edge that is not a bridge if you can. So if you can't choose an edge that's not a bridge, you just choose the bridge. But if you can choose an edge that's not a bridge, choose an edge that's not a bridge. So in this case, where we're starting here is A. There is only one edge coming out. If I remove that edge, you see you disconnect the graph into two pieces, one just with A as an isolated vertex and everything else. So there's only one edge coming from A, and it is a bridge. I don't have any choices. I have to choose that, and I will label that 1. And now I'm at B. Now, let me show you what I do when I do this, because I'm already kind of in it, but let me show you what I do when I do this. What I do is I make a copy of my graph, and I put it over here. And this is my working copy. This is just a copy that helps me get things done. Scratch paper, if you will. And after I've chosen a path on the left-hand side, where I've chosen one, I remove it on the right-hand side. So now I'm at vertex B, and I just do exactly what I did from B, looking at the right-hand side, as I don't want to re-choose. I don't want to choose something I've already chosen before, because I'm supposed to be getting an Euler path where I don't repeat edges. So I choose amongst these three edges, but I have to be careful. I need to choose something that's not a bridge if I have that choice. Well, this edge is a bridge. I don't want to choose it. So that means I can choose this edge or this edge. Both of those are not a bridge of the remaining graph. So I will, and it's always a bridge of the remaining graph, not just of the original graph. So I will choose, I don't know, the one down here. So they'll choose BC. Great. I've chosen BC, I've numbered it on my left-hand side, and now I'm going to remove it from my right-hand side, from my working copy. And now at C, I'm going to look, and I'm going to look at all my options of the edges coming out of C. It turns out there's only one. It is actually a bridge of the remaining graph because it isolates C, but I have to choose it. It's the only thing I've got. I choose it, and I erase it on in the working copy. Now I'm at E, so I'm traveled so far. Now I'm at E, but I'm at E really in this working copy. I've only got one edge. I have to choose it. I choose it. That's 4. I erase it in my working copy. Again, I only have one choice. That's 5. And so I erase it and I'm done. And now you can kind of, if you want, you can just delete the right-hand side and you can write out what's happened. I mean, let's just double check when we trace it out. We trace it, we go 1, 2, 3, 4, 5. That is a path, and nothing's overlapping, and it hits every single edge of the graph. That means it's an Euler path. If I were to write it out in terms of a sequence of vertices, I would write A, B, C, E, B, D. And that would be an Euler's path for this example. Now, if I was looking for a circuit, well, as we saw a second ago, because of Euler's theorem, not all of the vertices are even. Therefore, there is no Euler circuit. So that's not something worth looking for if you know that it doesn't exist. However, if all of the vertices are even, then there's Fleury's algorithm also applies. You just have to take into account that you're going to be ending. I mean, you basically just need to use this algorithm that we just used and just choose a starting point. That's basically it. But again, you need to assume that it's connected and that all of the vertices are even. All right, hopefully this review helped a little bit. Good luck.